Continuing cryosphere discussion about glaciers. So, as the glacier warms, the base condition could change from cold to warm and cause a significant surge or advance, making it look like the glacier was growing, but really it was losing mass as even more surface area enters the zone of ablation. Anyway, glaciers can be tricky. There have been many periods when glaciers all over the world have gained mass and advanced. These periods are called glacial intervals. Their periods have major continental glaciations too, which create ice sheets. In contrast, interglacial intervals are warmer periods with less glaciations. There have been multiple advances and retreats of glaciers, which has been rare during the Earth's 4.6 billion history, but frequent in the last 1 billion years. So let me tell you about continental ice sheets. They are a bit different than what we normally think of when we think of glaciers. Glaciers, in my mind, generally start high up in the mountains and flow downhill. Ice sheets are more like a pile that still flows downhill. No need for mountains. For an example, think of peanut butter on a hot day. You are bored, and so you decide to make a pile of peanut butter on the table. You spoon the peanut butter onto the table in the same general spot, and notice that the peanut butter flows slowly away from the center. If your peanut butter is too thick for this, think of cold honey or some other liquid with high viscosity. Now just think of this pile as snow transformed to ice that slowly accumulates and flows out from the area of accumulation towards areas of ablation, where it melts and calves, and the ice finally ends in a wet, soggy mess. Before we leave this slide, look at the image. Along the x-axis, the bottom axis, we have years before present, going back 650,000 years. Along the y-axis, or vertical axis, we have carbon dioxide in parts per million. On the graph, we have a zigzaggy line that goes above and below the 230 parts per million carbon dioxide line. Where the line is above the 230 line, it is marked in yellow. And where it is below the 230 line, it is marked in blue. Where there is a large section of yellow, carbon dioxide concentrations were generally higher. The atmosphere was generally warmer, and glaciers and ice sheets lost. We had an interglacial episode. On the graph, several interglacial episodes are named. Where there is a large section of blue, carbon dioxide concentrations were generally lower. The atmosphere was generally cooler, and glaciers and ice sheets won. We had a glacial episode. According to the graph, how many transitions have there been between glacial and interglacial episodes over the past 650,000 years? I'll repeat. How many major transitions have there been between glacial and interglacial episodes over the past 650,000 years? I counted 13. Would you agree? Who's heard of the Pleistocene? The Pleistocene epoch stretches over the past 2.5 million years. It covers the last series of glacial and interglacial periods, with multiple ice ages. During glacial periods, glaciers and ice sheets covered 30% of Earth, as compared to only 10% today. The last glacial maximum, i.e. when glaciers were at their biggest, was about 21,000 years ago, depending where you look and which dating techniques you use. Global sea level was more than 100 meters, or 330 feet lower than today. These images show the approximate extent of continental ice at the last glacial maximum and the present. Can you guess which is which? This image also depicts the extent of continental ice at the last glacial maximum. We have the Greenland ice sheet which is still there today. We have the Laurentide ice sheet that piled up over and pushed down the Hudson Bay. The ice sheet is now gone, but the land is still rebounding from being loaded with up to 50 kilometers of ice. And we also have the Cordilleran ice sheet in the Rockies. I like this image because it shows a corridor where animals, and perhaps early humans, could migrate from Russia, Asia, into the Americas. Early humans and present-day humans that live near glaciers are familiar with their associated hazards. Unfortunately, I have never lived by a glacier, but I know that glacier movement and melting have been responsible for property damage, injuries, and deaths. People can fall into deep crevasses. Glacial ice can fall from above, can expand to overrun villages, etc. Produce an ice jam to cause flooding. Blocks of ice may fall off in avalanches. Calving produces icebergs in the ocean. When glaciers are on top of an active volcano, the volcano can melt massive amounts of the glacier, which then saturates the large amounts of soil and volcanic debris that can flow down the mountain, creating a lahar, which is a fancy name for mass movement of volcanic debris. In the map of the Yungay, Peru area, these mass movements are called avalanches, one in 1962 and one in 1970. Based on the map, it looks like the people in Yungay, Ranchahirca, and Matakoto got lucky in 1962, but not in 1970. Consider this. Could the disaster in 1970 have been mitigated prior to the lahar flow? What could have been done? I'll repeat. Could the disaster in 1970 have been mitigated prior to the lahar flow? What could have been done? Write me an email if you'd like to share your thoughts. 12.4. How we study climate change and make predictions. Our instrumental record is not very long compared to the history of the Earth. Measurements of temperature made directly, i.e. with a thermometer, only started about 1860. Carbon dioxide measurements from about 1960. And solar energy has only been measured over the past several decades. Our historical record stretches further back but doesn't give us exact temperature measurements or carbon dioxide concentrations. Historical records include written recollections from such sources as books, newspapers, journal articles, personal journals, ship's logs, farmers' crop records, etc. But to understand long-term climate trends, we need more data as well as data from even further in the past. To get this data, we turn to the paleoproxy record. Paleo means older. Proxy means to have the authority to represent someone else, or in this case, something. The old thing that the data represents is ancient climate. Again, proxy data can be correlated with climate. However, the data is not a direct measurement of temperature, but provide the climate record that predates the historical and instrumental records. There are several sources of paleoproxy climate data. The first one we will discuss is tree rings or dendroclimatology, and the climate data provided by tree rings. This data extends back more than 10,000 years. The image depicts how we put together climate data from tree rings. Let's first review what tree rings mean. I bet you already know this. So, in climates with distinct growing seasons, trees grow when it's warm and take a break when it's cold. When the trees grow, they add a light layer of wood. When they take a break, they add a dark line. When added together, the light and dark layer represent 1 year. Most trees grow most years, so just by counting the number of light layers or dark lines, you get a time span. When growing conditions are optimal for the type of tree, the light layer is nice and thick. When growing conditions are poor, the light layer is thin. Most trees like warm, moist conditions for growing. So a large light ring would indicate what about the spring and summer that year? Right, warm and moist spring and summer. What would a thin light ring indicate? Right again, cooler and drier. What would several thin light rings indicate? Maybe a multiple year drought. What would a charred layer indicate? Wildfire, of course. And a diseased layer? So you see, these tree rings can contain a lot of climate information. And so I said that the dendroclimate record goes back about 10,000 years. You have probably seen already that the 10,000 years is not from one tree, but from several trees from overlapping generations. In the picture, we have a living tree, a dead tree, and a log beam, and a Native American home, which is also dead, but older dead. An analogy would be like a kid, a parent, and a grandparent, if that is easier for you to picture. More and more generations are added to the tree climate record, and these overlapping generations extend back over 10,000 years. To get the age of the climate information in each ring, the dendroclimatologist, or more likely the graduate student, would first match up distinctive patterns in the tree rings, and then start counting tree rings back from the present. To check and verify their counting skills, carbon-14 measurements are taken every once in a while. Carbon-14 is a radioactive element that is created in our atmosphere by solar radiation. Every living thing incorporates carbon into their bodies as long as they are living, and a teensy tiny bit of that carbon is the radioactive carbon-14. As soon as you, or whatever other living organism dies, that carbon-14 begins to decay. If we know about how much carbon-14 you are supposed to have, we can measure how much the dead you has, and we can calculate out how much is missing. Just subtract. And since we know the rate of carbon-14 decay, we can also calculate out how long it took for the carbon-14 that is missing to decay, and therefore know how long you have not been adding more carbon to your system. Or in other words, we can determine how long you have been dead. For trees, we can figure out how long each tree ring has not been growing, and so know the year that it grew. We will talk more about carbon-14 later. Sediment cores from depositional basins, such as lakes, can also give us climatological information. We get the climate information from the amount, type, and number of fossils, and chemicals in the preserved water, sediments themselves, and fossils. These are all interpreted to provide data on climate change. So what do I mean? The amount of sediment deposited will vary due to stuff. Think of a dry period, where there be more or less sediment blowing around and available for deposition. If you said more, you're right. Next, think of a lake near a glacier. There are usually lots of lakes there. Now think of all the ground up rocks underneath and even on a glacier. Now think what happens to all the ground up rock as a glacier melts. Would a lot of sediment be deposited when there was general glacial melting? As you can imagine, glaciers melt more in the summer and not so much in the winter. In fact, I bet you'd know that lakes near a glacier usually are covered with ice in the winter. This creates what is known as glacial varves. They are almost like tree rings. This is an image of the sediment that settled at the bottom of ancient glacial Lake Missoula.